Okay, let's pick up where we ended from the last video. Now we're going to work on example 2. Actually, example 2 is a lot easier than the first one. Here we have a class with 100 students. They have the following frequency distribution of blood type. Let me see where. So here we have A, B, and O. So there are 4 blood types. A randomly select student does not have blood O. So this is a condition. So we're going to cross out type O students. What is the probability that a student has blood type AB? There are 35 students with blood type AB. And given what's happened, so given the student does not have blood O, so the remaining total will be 100 minus 10. So we have 90 students. Okay, so basically by conditioning, we have a smaller sample space. The original one is A, B, and O. Okay, now we do conditioning. By conditioning, we have A, B, and AB, right? So type O is excluded. So that's the conditional probability. So let's go to the next one. In example 3, Stacy is taking an English class and a history class. There are 3 possible events. E stands for A in English class, H stands for A in history class, B stands for both. And we know some probabilities here. We have E, H, and B. What is the probability that Stacy gets at least an A in her 2 classes? So the information is nice enough. We already have everything written down in beautiful mathematical notations. The only question so far right now is how we are going to convert the question into a math type. Excuse me. So what we are trying to do is draw a sample space. This is E. In between, the common part is B. What we want to know is the probability that she gets at least 1A. So what are the possibilities? She could be E, but not H, right? Which means she gets an A from English class, but not from history. Or not A from English, but A from history. Both. That is B. So there are 3 possibilities, right? So which means, let me use a different color. The first one is this, right? So it's E intersect H complement. The second one is here. And finally, the last one, let's pick this color. This is the joined part, right? So we are trying to calculate the probability for all shaded areas, right? So this is basically to say we are trying to calculate the union. Right, that is exactly the definition of union. We can apply the so-called addition formula. Right, so we add E and H and then minus the joined part, because by doing addition, we add the common part twice, right? Because B is in E and in H as well. So when we add them, we actually add b twice. So we need to subtract 1 out in order to get the entire union. Okay, so it's very easy to get the result. It's actually 65%. Okay, example 4. So here we have an insurance company. It records that 12% of teenagers have been ticketed for speeding, 9% for running a red light. If 4% have been ticketed for both, what is the probability that a teenager driver has been issued a ticket for speeding, but not for running a red light? So again, we need to process the information first, right? Here we have 2 features. A is about speeding. Let me use the color I prefer more. So here we have 2 features. A is about speeding. So we call A the speeding set. The second feature is about running through a red light. So I have 2. Next, let's interpolate the probabilities. 12% have speeding tickets, so PA is 12%. 9% went through a red light, so this is 9%. 4 has been ticketed for both. Both is the intersection. So what do we want to know? So basically we have done the first step, the second step. The third one is to convert the question into a probability notation. We want to know a teenager has been issued a ticket for speeding, but not for running through the red light. So it will be A minus B. Okay, so sometimes I think it's more common for people to use backslash to write the difference. So in other words, when we draw this graph, here's A, here's B. Okay, what we want to know is the portion of A that does not intersect with B. So in other words, what we want to know is A intersect B complement, because that is the part of A that has nothing to do with B, right? So it's not in B. Right, it's very easy to see that A can be separated into 2 disjoint parts. The first part is the probability we are trying to calculate. The second part is the intersection part, right? So we know A, we know the intersection, so we immediately know this is just the 8%. So the next one, suppose it is known that 23% of countries are classified as large, 19% are classified as developed, 17 are both. What is the probability that a country selected at random is not classified as either large or developed? So again, we can set A as large, B as developed. Right? So we know PA is 23%, PB is 19%, and P of A intersect B is 17%. Okay, in the next step, we are trying to calculate that is not, right? Not large or developed. So we want to know the intersection of A complement and B complement. So to see what it is, you can actually draw a graph. Here I directly claim it is the complement of A union B. Okay, if you are not fully convinced what it is, again, we can always draw the graph. Here's A, here's B. What do we want to know? We want to calculate A intersect A complement intersect B complement. So that is this part. Right. So it's rather complicated to directly compute the area of the shaded part by blue, right? But we know it is the complement of the union, right? Because we know inside is exactly the union of A and B. And of course, what we are trying to calculate is the complement part of it, right? So because it's a complement, it's 1 minus the union. We know how to calculate the union, right, by applying the addition formula, right? So you can do the calculation. The result is 75%. Okay, moving on. The next one is it's on conditional probability. Assuming that 75% students studied for a test. So the first feature. So feature 1 is whether somebody has. Let's not do it yet. Let's keep reading. The next one we talk about is if 40% of those who study get an A, but only 10% of those who don't study get an A. So here we have two features, right? The first one is about the result, right? A student can get an A or not an A. So let's say set A is grade A. Okay, set B is about whether the student studied for the exam or not. So assume the positive case for B. So if the set of students who studied, then the complement will be those who didn't study. And then let's interpolate. Okay, well, it's good to know 3/4 of the students studied for the exam. And even better, those who studied are more likely to get an A, actually 4 times bigger than those who didn't study. Right. So step 2 is done. We are able to transfer all the information into probability notations. Step 3, what do I try to do? Probability that someone who gets A and actually studied for B. So we want to know what is the probability that the student studied for the exam given that this student gets A. So we want to know the probability of B given A. So this formula we have already applied several times. And so we want to know the how many of them have. So this is what is the chance of getting grade A. To do this, we are going to need the condition from both conditional probabilities. So from there, we know A intersect B, it is PB times PA given B, right? So we know PB, we know PA given B. So we know the first intersection, that is 75% times 40%. So this will be 30%. So applying the same kind of formula, but to the next one, this will be B complement PA given B complement, right? So we know PB, so we know the complement is nothing but 25%, and here is 10%. So this is 2.5%, right? So by adding those two together, we get the probability of A. Again, by applying the total probability formula, right? PA is A intersect B plus A intersect B complement. So it will be 32.5%. Okay, so this will be 30 divided by 32 plus 32.5%. So you get the result, it's about 92%. So the example 7 is different from all the previous ones. So we're going to take a closer look. In a certain lottery, you have 70% chance of winning $5, 25% of winning $10, and 5% of winning $100. Okay, so this is a wonderful lottery. Of course, supposedly you're going to pay more than $2 for this lottery for sure. A standard way is to think about what is your sample space, right? So here we have 3 possible scenarios. We can call them omega 1, omega 2, and omega 3. And we can have a probability as P1 is 70%, P2 is 25%, and P3 is 5%. Okay, and here we have a random variable. Okay, we can call it the amount of winning from the lottery. So we have X. So X omega 1 is, let's call it X1 is 5. So for the same reason, we can define X2 as 10, X3 as 100, right? So we have a random variable that takes 3 possible values, 5, 10, and 100. They are distinctive, and each with the probabilities known to us, right? So that is P1, P2, P3. If you want, you can write down the corresponding probability, right, for X. So we know Px equals Xi, it's simply Pi. Okay. CDF. CDF stands for cumulative probability function, distribution function. And the definition is the probability that X random variable less than or equal to. So here, less than or equal to, okay? So of course, you need to discuss all possible values, okay? It's very common to miss some of the results because it's possible that you do not exhaust all the possibilities. So here X, small x, can be any real number. So you start with, the first value we have is 5. So if this small x is less than 5, it's 0, right? Because nothing will happen below 5. Okay, anything below 5, there is no chance of happening. So the probability is 0. The next layer is greater than 5, but less than 10. For any x greater than or equal to. So here the inclusion here is included, okay? So that's important. Including 5, but excluding 10. Within this range, there's only one possibility, right? That's omega 1. And we know the probability of omega 1 is 70%. Going to the next level is greater than or equal to 10, but less than 100. For anything between 10 and 100, there are 2 possible scenarios, right? Omega 1 and omega 2, and adding them together, because they do not happen at the same time, so they are disjoint. So it's actually 95%. And finally, for x greater than 100, is 100%. So CDF, the cumulative distribution function, is a function that grows from 0 to 1, okay? It's possible that it may stay flat, but it will not go down. So it's increasing in the weak sense. So let's call it 5, 10, here's 100. Of course, it's not exactly to the scale of the corresponding values. For anything below 5, it's 0, and here it's empty. Okay, then I jump to 70%. So this level is 70%. Okay, I stay at this level until 10. At point 10, I jump to the next level, which is 95%. So this is 95%. Okay, finally at 100%, at the value of 100, I jump to 100%, and of course, I will stay at 100% forever. Probability will never be greater than 1. So 100% is the maximum. So this is the graph of it. And then I want to calculate the expected, this is the variance or standard deviation. So I'm going to start with the expected value. So it will be value times the corresponding probability plus 100 times 5%. Okay, there are different ways of calculating the variance, right? So you can try this. This is defined as x minus the mean, which means I'm going to do 5 minus the mean, which is 11, times the probability of 5, plus 10 minus 11 times the probability of 10, then finally 100 minus 11 times the probability of 100. Okay, this is one way. Sometimes, in particular for discrete, it's probably easier to calculate the second moment, right? So it's 5 squared times 70% plus 10 squared times 25% plus 100 squared times 5%, right? And then I know my variance is my second moment, which is the expected value of the square minus the square of the first moment, right? So this might be easier, but they are around the same level of difficulty. So example 8 is about a special formula. Here I can give you. So try to prove this result, okay? So A and B are two constants. Y is a random variable. It shouldn't be complicated for discrete probabilities. You just need to write down the summation, and you should be able to see this result. Okay. Question 9. It's somehow interesting. Okay. Here, someone is going to toss a fair coin 200 times. You watched the first 40 tosses and noticed the 16 heads. But then, of course, you got bored and left. Okay, what would you expect the total of heads after your friend finished 200 tosses? So he's going to toss to toss the coin 200 times. You already observed the result for the first 40 ones, and the number of head is 16. They are 160 to go. Okay, you haven't watched. But this is a fair coin. So the chance of getting a head is the same as that of getting a tail, okay, 50%. Given that there's a 50% of a chance of getting a head and someone tossed 160 times, what do you expect? The total number of tossing times the probability, right? So you expect to see 80 heads for the remaining 160. So the answer is, what do you already observe plus what do you expect to see? So 96. Okay, later on we will see this part is actually a binomial distribution with n equals 160 with p equals 50%. We will actually learn this result later on. The next one asks you to calculate mean and the standard deviation. Here, the only thing I want to talk about is independent. So there are many definitions, slightly different definitions for independency. So here, what x and y. So let's say x and y are two random variables. X and y are independent if x and y are called independent if the correlation is 0, or equivalently, you can see the covariance is 0, or you can also see the expected value of right. This is quite often used as the definition for independent random variables. That is, the expected value of the product equals the product of expected values. Okay. Once this is clear, then it is straightforward. If we want to know the sum, so here we can define x as the result of die A, y as the result of die B, and those are special ones, right? So x can be 1 or 3. And what is the probability? Phase 1, well, there's only one phase with value 1. So the probability is 1/6. There are 5 phases with 3. So the probability is 5/6. In the meantime, for die B, the result is either 2, and the probability is 4/6, or 6 with probability 2/6. Right? So it's easy to calculate the expected value for x and y and their corresponding variance. Right? The sum is simply, and the variance is the variance of x plus the variance of y plus 2 times their covariance. The formula for variance is something similar to the square of x plus y, right? So the x squared plus y squared plus 2xy. So this is something similar. Because they are independent, so this part is 0 because of the independent condition, right? So it's easy to do once you know the variance of x and y. Example here is about the Pepsi's running a sales promotion in which 12 of them is 12% of the bottles has a free logo. What is the probability that you win at least one in a 6-pack? So this is often tested with a keyword, at least one, right? So let's say A, let's use A to denote at least one. Okay, of course, it's in a 6-pack. Right? We want to calculate A. But A is somehow difficult to do, right? Because it says at least one. At least one can include many scenarios, right? It can be exactly 1, exactly 2, exactly 3, all the way to exactly 6. But the opposite side is very simple, right? The complement, what is the complement? At least 1. The complement is none, right? And what is the probability of not seeing any of them? We know there is 12% chance of seeing a free logo. So not seeing a free logo will be 88%. And you can assume each one is independent of each other. And you see 6 of them with no free logo. So you raise the power to 6, right? So that's what we do. Example 12 is actually regarding binomial distribution. Which we will talk about, of course, in the actual chapter 1. The notation is we have 30, we have tried 30 times. Here the police stopped 30 vehicles. The probability is 83%. Okay, and you want to know the variance of the driver, right? So we will learn some formula. So I can tell you the formula is NPQ. Okay, with Q is 1 minus P. Okay, we will derive this formula. So it's a simple question once you know the formula. The next one is about geometric distribution. So again, we will study this. So I will leave this once we cover the corresponding topic. If you want to know, you can study this on your own, right? Be a little bit more independent to search what is a geometric distribution. Example 14 is about a Poisson distribution, a very popular one to model the arrivals. For instance, here we have a probability. Usually we use lambda to denote. Okay. This is regarding Poisson distribution. The next one is a tennis player makes a successful first serve 64% of time. She serves 6 times. So as long as you see things like this, you should have a general idea that we are talking about a binomial distribution. Again, if you don't know, that's okay. We will actually learn what binomial distribution is in the coming weeks. So finally, I want to talk a little of this. So of course, you first need to build a model, and I can tell you the model is binomial. Once you know the model, you are able to calculate the mean, which is 124.8, and the standard deviation, sigma x denotes the standard deviation. It's about 5.24, okay? Assuming you know that for the moment. The question asks, what is the probability that they found at least 30 not wearing the seatbelt? So we want to know at least 30. At least 30, which means this is less than, right? Because X is the number of drivers who wear seatbelt. So if you want to know the number who do not wear seatbelts is at least 30, which means those who wear seatbelts is less than 130, right? So this is binomial, okay? So technically speaking, you can actually use computer to calculate this because you can break this down as 0, 1, 2, 3, all the way to 130, right? Because the number of drivers is definitely an integer, right? It's not 1.5, 2.1, right? So it will be one of those numbers. and you can calculate each and every one of them, and then you sum up. I from 0 to 100 is actually not. So here is 130, but here is 129. Okay, so I sum from 0 to 129, the probability that x equals I. Okay, I do have the formula for binomial on how to calculate this. So technically speaking, I can quickly use a program to do the calculations, right? So actually, they have the direct CDF built in, so you can directly get the true result. But we don't want to do that. We want to apply normal approximation. So what we do is, from here, we assume x is close to a normal distribution with the given mean and the given variance. Okay, and once we have that, how do we calculate? We do the so-called standardization. We minus or subtract the mean, divide by standard deviation. So now it will be 130 minus 124.8 divided by 5.24. Okay, so that is z less than about 99. So z is a standard normal distribution with 0 mean, 1 variance. Okay, we have the table for all the results. So from here, you can check the table. It's about 0, 3, 99. Okay, that is the end of this exercise. Okay, I think that's good for today, and we will next time when we continue, we will start the actual chapter 1.